For thousands of years, we looked up and thought we understood. The stars were fixed, the heavens were eternal. The universe, vast as it seemed, operated by rules we could grasp. Then we looked closer. We built better instruments. We measured more carefully. And each time we did, the universe became stranger. Heliocentrism shattered our place at the center. Relativity bent space and time. Quantum mechanics revealed that reality at its smallest scales operates by rules that defy common sense. Each discovery forced us to admit that what we thought we knew was incomplete, sometimes entirely wrong. We are approaching that threshold again. NASA's next generation of missions is not about exploring new planets or mapping distant moons. This is different. These missions are designed to confront gaps in our understanding so fundamental that filling them could rewrite what we think existence is. They are not routine. They are not incremental. They represent a shift in what space exploration means. For decades, we have been sending instruments into space to see farther, to observe objects billions of light years away, to peer back in time toward the moments after the Big Bang. And what we found was not clarity, it was contradiction. Galaxies rotate too fast. According to the gravity we understand, the stars at their edges should fly off into space, but they don't. Something is holding them together, something we cannot see. The universe is expanding, that much we knew. But it should be slowing down, pulled back by the gravity of all the matter within it. Instead, it is accelerating, speeding up, driven by something we have named but do not comprehend. Massive structures exist where our models say they should not. Galaxy clusters, walls of galaxies stretching across hundreds of millions of light years, formed too quickly, too early, in a universe that was supposed to be more chaotic, more evenly spread. These are not minor discrepancies. They are not rounding errors or measurement noise. They are signals that our physics is incomplete, that the universe operates by rules we have not yet discovered, and NASA's upcoming missions are being built specifically to find those rules. New space telescopes are launching, not to replace the ones we have, but to see what those cannot. Instruments designed to observe wavelengths invisible to human eyes. Infrared, X-ray, microwave. Each wavelength reveals a different layer of reality, structures and processes that visible light alone could never show. Some of these missions will stare at the same patch of sky for months, not scanning, not surveying, just watching. Collecting photons from objects so distant and faint that only patient, uninterrupted observation can reveal them. Freed from Earth's atmosphere, from its light pollution, from the interference of our planet's magnetic field, these instruments will achieve a sensitivity unprecedented in the history of astronomy. They will map dark matter, not directly. You cannot photograph dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can measure. But it has mass, and mass bends space. Light traveling through that bent space is distorted, stretched, magnified. By analyzing those distortions across millions of galaxies, these missions will construct maps of where dark matter exists, how it clumps, how it flows, how it shaped the formation of everything we see. They will measure dark energy's behavior over time. Right now, we know dark energy is driving the accelerated expansion of the universe, but we do not know if it has always been constant or if its strength is changing. If it is increasing, the future of the universe becomes far more violent. If it is decreasing, our models are wrong in ways we have not anticipated. These missions will track the expansion rate at different points in cosmic history with enough precision to detect changes that current instruments cannot resolve. They will observe the first galaxies, the very first structures to condense out of the primordial gas after the Big Bang. Galaxies that formed when the universe was only a few 100 million years old, in an era we have never directly seen. How those galaxies formed, how quickly stars ignited within them, how they grew and merged, will tell us whether our theories of structure formation are correct or whether something crucial is missing. And they will test whether the laws of physics are universal, whether gravity behaves the same way in distant galaxies as it does here, whether the constants we rely on, the speed of light, the strength of fundamental forces are truly constant or subtly different across space and time. If they are different, everything changes. If they are the same everywhere, that is also profound. It means the universe, for all its strangeness, operates by consistent rules. This matters more than it might seem. Every technological revolution in human history emerged from fundamental discoveries that seemed, at the time, abstract, theoretical, disconnected from daily life. Electromagnetism was a curiosity before it became the foundation of modern civilization. Quantum mechanics seemed like philosophical speculation before it enabled transistors, lasers, and the digital age. Relativity was an esoteric theory about space and time before it became essential for GPS satellites. We do not know what understanding dark matter and dark energy will unlock. We do not know what technologies might emerge from a deeper grasp of gravity or the nature of space. But history suggests that when we answer fundamental questions about how reality works, the consequences are never small. Changing our understanding of these forces would not just rewrite textbooks. It would redefine humanity's relationship to the universe. It would shift our conception of what is possible, what is knowable, and what our place in all of this actually means. NASA's missions may confirm theories that currently exist only as mathematical speculation. Models that predict extra dimensions, modifications to gravity, interactions between dark matter and dark energy, or structures in space-time we have never imagined. Some of these ideas will be validated, others will be discarded, and some will reveal entirely new questions we did not know to ask. This uncertainty is not a flaw, it is the point. Real science does not advance by confirming what we already believe. It advances by exposing what we do not know and then systematically attempting to find out. The most important discoveries are the ones that surprise us. The data that does not fit, the observations that force us to reconsider everything. These missions are designed to find those moments. There will be silence in the data, long stretches where nothing changes, where instruments collect light, pixel by pixel, waiting for patterns to emerge. This is not dramatic, it is not fast. It is meticulous, patient work conducted across years, sometimes decades. But somewhere in that data will be an answer, or a deeper question. Past missions mapped the solar system. They sent probes to planets, moons, asteroids. They cataloged surfaces, atmospheres, compositions. They told us what is out there, where things are, what they are made of. These new missions are attempting something else. They are trying to map reality itself, to understand not just where objects are, but why they move the way they do, why they exist at all, what forces govern them, what structure underlies everything. This is a different kind of exploration, less about place, more about truth, and the results may not be comforting. The universe these missions reveal could be far stranger than we currently imagine, colder, more isolated, governed by processes that have no analog in human experience. It could show us that the matter we are made of, the stars we see, the galaxies we study, are an insignificant fraction of what exists, that most of reality is invisible, intangible, forever beyond our direct reach. Or it could reveal unexpected order, patterns in the distribution of dark matter, regularities in the behavior of dark energy, structures that suggest the universe, for all its chaos, operates with a kind of logic we have not yet grasped. We do not know which it will be, but we will find out. Humanity has stood at this edge before, the edge of knowledge, the moment just before understanding shifts. When Copernicus proposed that Earth was not the center, it felt wrong. It violated intuition. It challenged every assumption about our importance. But it was true. When Einstein showed that time and space were not fixed, that they bent and stretched, it seemed impossible. But it was true. When quantum mechanics revealed that particles could be in multiple states at once, that observation itself changed outcomes. It defied logic. But it was true. Each time reality turned out to be stranger than we thought. Each time, we adjusted. We learned to live in a universe that did not match our expectations. And each time, that new understanding opened doors we did not know existed. We are at that edge again. NASA's next missions will send back data, numbers, images, spectra. light curves, the raw material of science, and scientists will analyze that data. They will compare it to predictions. They will build models. They will argue. They will test. And slowly, over months and years, a picture will emerge. That picture may confirm what we suspect. It may overturn what we believe. It may raise questions we are not prepared to answer, but it will be real. And once we see it, we cannot unsee it. The universe may look the same after these missions complete. The stars will still shine. Galaxies will still turn. Space will still expand. But we will not see ourselves the same way, because understanding changes everything. These missions are not about rockets. They are not about technology. They are about perspective, about standing at the boundary of what is known and stepping across, about admitting that the universe is larger, deeper, and more complex than we have accounted for, and then doing the work to understand it anyway. The data is coming, and when it arrives, we may discover that everything we thought was solid is only an approximation, that the ground beneath our theories was never as firm as we believed, that the universe has been telling us something all along. We just were not listening carefully enough.